Okay, so hi everyone, welcome to another MLFL. This week we're really excited to have Mireshghallah. She's a third year CS PhD student at UC San Diego, and she received a BSc in computer science from Sharif University of Technology in 2018. She's also a recipient of the National Center for Women in IT Aspirations in Computing Award, which she received in 2020 on her work in lightweight privacy preserving ML. At UCSD, she's focusing on designing practical and low overhead privacy preserving solutions for deployed cloud-based deep learning models. She was also a research intern at at Microsoft Research AI in summer 2020. And out there, she worked on privacy preserving text generation. So without further ado, let's get started. Fatima, over to you.
Thank you so much for the introduction. So I'm Fatima, and I'm going to be talking about some of my recent work on privacy and fairness in deep neural network inference. So I'll first provide some background and motivation into what do I mean by like inference privacy, prediction privacy, and what are the existing works, how do they compare to each other, and then like what is differential privacy and how does differential privacy fit in this picture. And then I'll explain two of my works in this area, and finally I'll explain a more recent work that we did on the interplay of privacy and fairness, and then I'll conclude the talk. So what is prediction or inference privacy? We know that we're all using a lot of devices in our homes these days, or like at our workplace, and they're constantly collecting information, they're gathering information, and they're running queries for us. So we ask them to do something for us, to do a service like we call, I don't know, Alexa, and then it does something. So it's collecting our information and giving back a service. Now, this information is being sent to a maybe untrusted or compromised cloud. We don't always trust them. We would like to have some control over our own data. And then we run a service, and then they return the results back to us. Now, this information can be really sensitive, right? The information that we're sending to these service providers. It could be patient history, genetic data, or if it's at home, it could be our voice from the voice assistants, or it could be imagery from the security cameras. So most of these types of information, they have this sensitivity to them, and we would really like to take the control to us, take back the control and kind of be aware of what you're sharing and what could happen to it. So to put this more concretely and categorize the kind of works that are in this area, we know that deep learning or machine learning, the whole pipeline, we can kind of break it into three stages. The first is the data aggregation. We're collecting data to create some data sets that we then use for the training. And during the training, we're retrieving batches, we're training a model, and we're assessing it constantly to see like what's the best model and select it. And finally, once we have selected it, we deploy it for running prediction or inference. And there are many applications for robotics, for autonomous vehicles, the smart home devices, many different applications. Now, what my main focus will be in this talk is this last stage for deployment, that it basically means that I'm trying to focus on the privacy of the queries that we're sending to these deployed deep learning models and to just receive a service or a response. So we will be focusing on this last stage mainly. Now, what is the timeline of privacy and how did it form and like what is happening? So privacy, it's not new, right? Like we started putting curtains on our windows, that's when we started protecting our privacy, right? Because if we didn't care about privacy, we would just lock the doors or the windows. But putting curtains up, it kind of shows that we are caring about privacy. Now, more rigorously, works that focused on data aggregation privacy, on like creating data sets and how to query them while preserving the privacy of the people who are in the data set. They started emerging in 2002, 2006, works like K-anonymity and kind of the golden standard differential privacy was a paper in 2006. And there's a lot of work on this, right? There's like more than 5,000 papers, and it's actually gaining more, it's becoming more and more used these days. We're hearing that like different applications like Apple is using differential privacy, Google is using differential privacy for its keyboards. So we hear it around a lot, and it's basically something that a lot of people are deploying. Now, a bit later in 2011, when machine learning was being used more and it became more prevalent, works on privacy of machine learning were also emerging. So there are a lot of papers on that too, like over 600 papers, if you like go to Google Scholar and just look up the citations. And then after that, with deep learning and DNNs emerging, in 2016, the first works on the training, on private training of deep neural networks emerged. And there's also a lot of consequent work on those. And in 2017, 2018, we see like the first works on that focused on private inference. So trying to run predictions privately and kind of protecting the query of the users. And this is like compared to the previous ones, as you can see, it's like newer and it's also less worked on. It's like underexplored. Apart from all this academic research on this area, the international regulations are also trying to keep up with the technology. So we had GDPR in 2018. It's the General Data Protection Regulation, and it mandates whoever is using data from residents of Europe to kind of to adhere to certain regulations. And then in 2020, similar set of laws were enforced for California. It's called CCPA, the California Consumer Privacy Act, which basically also mandates the users of people who are using data from residents of California to give them certain rights, like the right to opt out, to just pull back their data. And if you've been to like California and like you use your phone, you get this notification that asks for some permissions because of the CCPA. So yeah, so this is like kind of the whole background and like what are the existing works part. So if there are any questions up to here.
Yeah, so there's one question. I'll just let him unmute. Prasanna?
Hey, yeah, can you hear me?
Yes.
It's a bit yeah.
Yeah, so can you explain the difference between DNN training privacy and DNN inference privacy? I didn't quite get that.
Mm-hmm. Yeah, sure. So let me actually go to this. Okay, I'll shortly explain it, but then I'll kind of explain it in more detail. But just to like quickly answer your question, so the training privacy focuses on protecting the privacy of the data that, or like the people who are contributing to the training of the model. So you have a data set imagine ImageNet, but like faces, right? Like something that has that is sensitive information. When you're training a model on that, the model learns. So it might also memorize the stuff. So that is the DNN training privacy. We don't want that to happen. We don't want the model to learn, or like we don't want the data to leak any information to the model. So it's about the data, it's about the privacy of people who are contributing to the training. But in inference, the model is kind of like, sometimes it's frozen, sometimes it's not, but the model is there, it's already deployed, and we don't care about like the training. We don't care about the information that leaks into the model from the training set. We only care about the data that you're sending to the model. So you call Alexa, let's assume that you have a picture of your face and you want to do smile detection. What the model needs is only your mouth, right? It doesn't need your face, it doesn't need your background. So what we're trying to do here is to like remove all these excessive features and just send what is needed for the inference. So here we don't care what the model is learning, we only care about the data that it needs to predict something. Did that help?
Yeah, he just replied yes. And
okay,
yeah,
thank you.
I think it's a small group. I'll just allow people to unmute.
Thanks.
Hopefully nothing will happen wrong. And we have one more question. Okay, never mind. It's not a question. Yeah, we can move on. Yeah.
Okay. So for inference privacy, most of the existing work is actually based using encryption. So either homomorphic encryption or secure multi-party computation, but all encryption mechanisms. And what encryption does, like in simple words, I don't really know much encryption myself. I don't know much crypto, but what it does is that it's more of a security mechanism than a privacy mechanism. It means that it's kind of whatever computation you're doing, the same thing happens, but it's now happening in the dark. You don't get to see it. You get to see like a jumbled encrypted format, but it's the same computation, right? It's the same data, and it's like the same set of, it's the exact same model, but it's all happening with this inside kind of like a box that you don't get to see what's happening there. So all these encryption-based mechanisms, what is good about them is that because it's the same computation, you're not losing utility, or you're using very small utility. So you get to have accurate results, and also you get to have perfect security, right? Because your data itself is not going to leak. But what the problem is that this type of computation is both more time consuming, so it takes much longer to get the same result. It has a huge slowdown. Like you can see here that it's from like 300 to 14,000 times a slowdown. And it brings the execution time from like 10 milliseconds. Normally it's around 10 to 100 milliseconds. It brings it to, you can see 3 seconds, 12 seconds. So it really increases the execution time. And for like real-time services that people are dealing with, and they're like for embedded devices that are not really critical in terms of security, this is really not good, right? You don't want to like tell something to Alexa and then wait 10 seconds to like get a response. And actually like the service level agreement is maximum is 100 milliseconds. So if you can't get the response in 100 milliseconds, then the users are not going to use whatever you have to offer. So all these kind of encryption-based mechanisms, they're really good. They provide a lot of security. They're good in terms of utility, but they cannot be deployed right now, like in real-time cases. So we have to kind of think of other things that are faster and that can respond, that have less of an overhead. And also apart from the execution time, these models, they also have a lot of communication in terms of gigabytes, because they also kind of, they make the data bigger. It's not just your image because of the encryption functions, it's now bigger. So it's in order of gigabytes. So you have to send gigabytes of data to the cloud to get a response back. Okay. So now, we saw that, okay, most of the work is actually encryption. So what is like differential privacy? Why aren't people using differential privacy here? Why is it mostly encryption? So what is differential privacy? In simple terms, what differential privacy tries to do is that if we assume we have two sets of data from two sets of people, and the only difference is that in one of the data sets, we have Alice's data. Let's assume it's medical records. We have medical records from a bunch of people, and Alice is in them. And then we remove Alice's data. So it's the same data set, only one person is missing now. And we train two models on these data. So one of them with Alice's data, the other one without. What differential privacy, if you want to show that we have differential privacy, what we need to do is to show that for any set of inputs to these models, the outputs are going to be very similar, right? Because we don't want to be able to differentiate the outputs. We want to say that, okay, like if Alice is in or if they're out, it doesn't make any difference in terms of the outputs. So Alice's data is basically not leaking into the model, or it's not leaking into the output. That's kind of what we're trying to show. So more concretely, if you have a randomized algorithm A, it satisfies epsilon differential privacy for data sets of D and D prime, which are neighboring, and neighboring means we remove one of them or change one of them, one of the data pertaining to a user. And then we show that for every possible output, the probability that these two models generate is bounded. So we get similar outputs. Now, using differential privacy for machine learning and deep learning, it can be done in any stage in the pipeline. So you can add this randomization, this noise to the input. You can add it to the gradient, so like gradient perturbation. You can add it to your objective function. You can add it to your labels, or you can actually add it to your output. So once you get the model, you just add some noise to the parameters. Now, there are some intricacies here, like for the objective function perturbation, the output perturbation, you can only do these when you have convex optimization. So you basically can't do them in deep neural networks because it's really hard to compute the sensitivity of the functions and some other things that you need to do. So basically, it's harder to do them there. So for deep learning, during the training, what they do is they do gradient perturbation. They add noise to the gradients so that data from the users is not encoded in the model. Because like assume that if you're using your keyboard and you're like typing your credit card or you're typing some personal information, like you're saying my credit card number is something, and if this was given to a model like this in raw format, then the model is very likely to memorize it. So if someone else who is using the model types in my credit card number is, they're going to get your credit card number. So that's what the kind of the training privacy means. You want to protect the people who are contributing. So they add noise to the gradient steering training to prevent this, to kind of obfuscate the information and, you know, hopefully provide this sense of like one person's contribution wouldn't really matter that much to the final output. Now, this is all for training, right? So for inference, the model is frozen. We don't really have anything to do with the model. So the only thing we can do is to perturb inputs. But what would it actually mean? Like, what are we trying to protect in inference with differential privacy? Again, inference privacy, we want to protect one person's query. So it really doesn't make much sense to say that, okay, I don't want this person's query to be similar to another person. Like, how do you define this neighboring data set? How do you define like a set that has one person and a set that doesn't have one person? So in general, like the definition is hard to adapt to this use case for like inference, because there you have this sense of collectiveness. There's a data set. And even if you kind of try to like figure out, okay, like any other possible data that looks similar, like if I'm sending my face then compared to all other faces, like what amount of noise should I add to protect some certain features? But what happens here is that because the noise is random and it has to be applied to all the pixels similarly, then you're not going to get good accuracy, right? Because it's going to be accuracy agnostic. You can't really enforce that within the image. So it's really like, it's either going to ruin the accuracy of the model or it's not going to provide any meaningful privacy. So people don't really, and it also like in general, it doesn't even make sense. So you don't really see any differential privacy papers for like for this use case of query or like prediction privacy. Okay, so a recap. We have this kind of trade-off between privacy and utility. If we try to just add noise agnostic, like without caring for accuracy, we're going to see a lot of loss there in order to get some privacy. Also, if we want to use encryption-based methods, we're going to get good privacy. We're going to have a lot of computational costs, but again, we're going to have good utility as well. So there is this three-dimensional trade-off, and what we're trying to do, and what there are other people who are trying to do it too, it's to kind of push this curve to some ideal that, okay, I don't want to have a lot of computational cost. I just want to be able to get better privacy with less loss in utility. So is there a question here?
Yeah, there's one question,
Yeah.
Akanksha.
Hi. Yeah. Hi. My question is, you said that at inference, differential privacy methods don't necessarily work.
Yeah.
But if you are applying such methods at the training end, do you actually need these methods at the inference end as well?
Okay. So this again goes back to the difference of these two. Once you're applying it for training, you're protecting the contributors' data, right? Like whatever data set was used, data from those people is protected. But then what about your query? Your query was not in the training set, right? Mm-hmm. And what we're basically trying to protect here is your query from the time it leaves your like cell phone or your device until it gets to the cloud. So this is kind of like what happens here. And then once it's also in the cloud, even when it goes in the neural network, like if someone has access to, because we're assuming that the neural network is frozen, right? It's already trained, it's frozen. And if someone has access to an intermediate representation, like they can get an activation which was activated using your data. If they can get this, there are many papers that show that they can reconstruct your query, they can reconstruct your image. So that's what we're trying to protect. We're trying to, it's a more local sense, right? We want to protect your query so that no matter who gets it, they can't really infer much, it doesn't leak any information. And at the same time, they can deliver good utility, right? It can be effective for that task. So yeah.
So it seems like this is a little bit tangential to differential privacy itself then, right? Or am I thinking of it wrong? Like, it is still privacy because you're concerned with not leaking information about that certain user that whose data is being inferenced on or whatever. But it's not that it's being part, like it's not about leaking information about.
Yeah, exactly. I get what you're saying. Yeah. So it is kind of related to that in an information theoretic sense. It's just that, so differential privacy does this with like data with like different people, right? So we don't want like across people, we don't want to leak information. But here what we're trying to do is kind of have differential privacy within the query, right? We don't want to like leak information that is inside one query. So yeah, it is kind of similar, yeah, but it's not the same thing. So that's why, yeah, that's why people don't use it like that.
Got it. Okay. Yeah. Thank you.
Thank you. Okay, so yeah, so this is what we're trying to do. And yeah, I'll now segue into the first paper, Shredder, which which is like on learning noise distributions empirically to protect inference privacy. Okay, so the key idea is to learn some noise patterns. Now, what do we mean by noise patterns, and like what are these noise patterns supposed to do? So assume that you have like your neural network. It's like normal neural network that you have, and normally during training, like what do? You feed in the input X, you get the output, and then you calculate the derivatives, you use chain rule to backpropagate, and then you like update your parameters, right? So this is what normally happens. Now, what we're thinking is that if we want to add some type of noise somewhere to protect people's privacy, but at the same time, we want to make sure that we have the utility. We could just add some random noise, right? And then like we have privacy, but then what happens to utility? We want to do it in a way that is context aware in terms of the like utility aware. So what we do is that we say that, okay, if this kind of backpropagation, if it works like this, what if we add noise to some layer in the network? So we cut the network, we like take the activations, we add this noise tensor there, and we freeze the entire network. So we're not changing any parameters. The only parameter that we are updating right now is that noise tensor. So we freeze the network, we are only updating the noise tensor. So now what happens to the backprop is that the backprop goes back to the noise tensor and it updates the noise tensor. So I will explain this in more detail, but this is the overall thing. So we're trying to train noise tensors. We're trying to train additive tensors that if you add them to this certain like activation, what happens is that the activation gets jumbled, but at the same time, the inference model, the main task, whatever it is, that one gives you good utility. So that's kind of the goal. And the good thing about like this kind of training the noise tensor with respect to whatever loss function the model had is that you can just put whatever activation function you had and you can just add this term for training the noise to it. And it's also non-intrusive to the model, so you don't really have to update your model at all. You're only training this one noise tensor, and you can do it for any layer. So it doesn't matter where you want to do it. Okay, so what would the execution model be then if we do this? What happens is that we have the neural network, we cut it into two parts. The first part that is less compute intensive, we'll execute it on the edge device, and the second part on the cloud. Now for this kind of cutting, we also did something. We calculated that like where is the best cutting point in terms of communication and computation. So we find the cutting point that incurs the least amount of overhead, and it actually sometimes ends up being faster compared to like not cutting at all. So this is not just arbitrarily cutting, you know, you're taking into account the communication and computation costs. And then once we have like our kind of cutting point, we calculate the first part, which is less compute intensive, on the edge device. We add our noise, and then we send it to the cloud. Now this noise, if it's only, if I'm learning one noise pattern and I'm just adding this noise all the time, then it doesn't really make sense, right? Like someone can find a noise and subtract it, and then they'll have the query. So that doesn't really make sense. So we have to make sure that the noise is actually random, and that is actually like information. Theoretically, it is decreasing the amount of information in the image. It's not just some static pattern that I'm just adding to everything. So what we do for the training of these noise sensors is that we partition the network, we initialize the noise sensor, we execute the first time, and then we add this noise. So for initializing the noise sensor, we randomly, like however you initialize your weights, you randomly initialize your noise sensor. We use Laplace and also Gaussian distributions to randomly initialize it. Both of them worked well, so it didn't really matter that much. And then what we do is we just carry out the normal execution of the model. Sorry. And then when we get the outputs, and then now that we have the outputs with this noise tensor, we check the accuracy. So if it's like the first kind of first iterations, then we're not going to have good accuracy. But if we continue this, then the noise tensor is being trained so that it kind of figures out how the model is actually working. So after after like a couple hundred iterations, the noise tensor is actually trained such that it can be added to like all the images and still give good accuracy. So if the accuracy is good, we take this noise tensor, we fit a Laplace distribution to it. So it's a tensor with dimensions, right? And you can take all the samples and fit a distribution to it. So we do this, and we also we like run a check to see how well the distribution is fit, because there's no guarantee, right? Maybe it doesn't like really fit well to any Laplace distribution. So we check it if there's if it fits well, we save it. If it doesn't, we throw it away and we initialize a new tensor. And we keep doing this until we collect like a set of like 20, 100, like the number really doesn't matter. Even one would be enough, but we actually collect multiples so that with time you can actually change your distributions. So you collect this, you get a distribution. So now you have a Laplace distribution with a certain like mean and standard deviation, and you save this. So that's what you save, and that's what you get. So you're saving these. You're not actually saving the pattern itself. And what happens is that if you only save the mean and the standard deviation, and you like next time when you're running inference, you just sample from those, then you might have a lot of loss in accuracy. So what we also save is the order of the elements. Like the first element has to be the biggest one. So once we sample from a Laplace distribution, we reorder them to match the saved distribution. So it's kind of like a multivariate Laplace distribution, because each of them is getting their own kind of order.
So Raj had a question.
Yeah.
I think it's quite relevant. Yeah, Raj. Yeah.
Yes.
Raj, we can't hear you. Okay, never mind. Oh yeah, we can hear you now. Okay, cool. Yeah.
Oh, that's interesting. My laptop lid was down. So thanks for the great talk. So sorry if I missed this. So what's stopping from the noise tensor to be zero? Like it could just like, since you are updating the noise tensor with gradients, what's stopping it to become all zeros?
Okay, I should have put the loss function first. So once we get to the loss function, you'll see the loss function is kind of like a regularizer. It tries to push the noise tensor elements to go up. So it has the summation of the elements of the noise tensor. So it's not going to be zero. Yeah. So the initialization is actually not zero, because we're taking samples from a Laplace distribution and we're placing them, and we're choosing a rather high standard deviation. So we don't initialize it to zero, and then our loss function incentivizes the magnitude of the elements to get higher. So they don't end up being zero. Yeah.
Thanks.
Sure. I will actually get to, there's the loss function. I should have put it earlier. Okay, so what is our loss function? Sorry, go on.
Oh yeah, we just had one more question. Joy?
Yes.
Hi, I just have a question. I think I'm misunderstanding. You're saying like if you go to the previous slide,
Yes.
there's a step where you say 6, update the noise tensor. The noise tensor is not being learned, right? It's just being sampled from a probability distribution.
Okay, so yeah, I mis-explained it kind of. What happens is that this noise tensor right now is a static, right? If the accuracy was not good, we update it like you update the weights. So you actually apply the update normally. Like you do backprop and you don't update anything else but this noise tensor. And then once you have a noise tensor that gives you good accuracy, you fit that to a distribution and you save it. And then like later on, so this is kind of a training phase, it's offline. Then once you're actually like sending queries to the cloud, you sample from it. But right now you're only learning the distributions that the model is actually robust to. It's kind of like anti-adversarial patterns. Like in adversarial examples, you learn stuff that make the model make mistake. Here, you're learning some patterns that actually the model can understand. And then once you have learned all your patterns, once you have learned all your distributions, then when someone is actually querying the cloud, you sample from that distribution, add to their query, and send it.
Okay, so the learning process is changing the parameters of the probability distribution you're sampling from to get a good one?
Exactly. So
okay.
this is a very good point. Yeah, here it's only changing the noise tensor. So what this paper does, it's kind of like it's generating examples of what noise tensors the model understands and then fits a distribution to them. But the next paper that I'll explain, it directly learns the model parameters. So that's the difference. Yeah.
And then just one more question.
Yeah.
You mentioned earlier that you freeze all of the other weights in the network except the one related to the noise tensor. How does that like affect the overall training process if nothing else is updating? Or do you at a certain point in time unfreeze them after you learned?
So this like what was really important for us here was that a user themselves can deploy this and they don't need any collaboration from the deployer. So you don't want like Amazon to update their model, right? You can only learn your own noise. So
wait, yeah, okay. It's inference, right? So you don't
really,
okay.
You don't change anything. Yeah. Okay, great. Really good points. Thank you. Okay, so our loss function, we want to have good utility and at the same time we want to protect privacy. So what we do is that we have two terms. One of them is for the utility, it's cross entropy loss. We have it there to make sure that you're not destroying the model's utility by our noise addition. And then we have this other term, which is kind of our privacy term, and it's there to maximize the standard deviation of the noise. So this incentivizes the model to actually increase its standard deviation. So like increase the amount of noise. So that's what we're doing. And then there's this alpha kind of a knob that allows us to trade off this utility and privacy. So if we increase it, we're going to have less utility, but we'll probably get better privacy because we are increasing the summation of our noise parameters. So there's also another extra case that we tried because we wanted to compare to a previous work. It was that we assume here, the good, like one kind of positive thing is that you only need to have your main task. So let it be like smile detection on an image. That's the task. That's what I want to save my utility for. And whatever information is irrelevant, I just want to add noise and I want to get rid of it, right? So what's good here is that you only need labels for that main task. But there are prior work that they try to protect against like a certain attacker. Like, okay, I want to protect, like I want to run smile detection successfully. I want to have utility for that. But then if there's an attacker that is trying to guess people's hair color or like people's gender, then I don't want that person to be successful. So they kind of, they target their protection towards a certain attribute. So they also have this extra label for like what the sensitive features are. Now, assuming we also have those, we can update our loss function to have this like kind of negative of the cross entropy loss for that attribute. So we say that, okay, apply the noise in such a way that this particular task for this, we also like, we get worse accuracy. So you can also just plug in this extra privacy term, but this was mostly only for the sake of comparison to that method. Yeah. Okay, so once we have collected our distributions, the training phase is over. That was offline, but now we want to deploy this like actually on our edge device and send our queries to the cloud. So what we do here is we choose one of the distributions we have collected. We take a sample from that distribution. We kind of like, we create our noise tensor. We reorder the elements based on the element order that we had saved. We inject this noise, we add it, and we send it to the cloud. And then we execute like this noisy activation is executed on the cloud. It returns some response. And yeah, we get our. So this is the setup. Like if you guys wanted to see how we actually like use an edge device and a cloud to like test everything. So I'm just going to skip over these so that I can get to the next paper. We tried a whole bunch of different data sets, CIFAR, SVHN, VGG face, ImageNet, all of these. And this is like the main result. It's that you have this accuracy privacy trade-off, and you can see here that that red line, it shows zero leakage. So if you want to like leak no information, you want to be close to that line. But as you see, like for the 20 news groups case, if you do that, you're going to have like 6-7% loss in accuracy. And like for MNIST, we actually like reached that point that you're not leaking anything, and then the accuracy was like, it was like a random classifier, which kind of makes sense. And we have this like for other data sets. So basically there's a trade-off, and this kind of looks similar to that ideal. I mean, it's not ideal, but it looks similar to that ideal graph that I showed at the beginning. And this is kind of like, this is also a very important result, that it was kind of the main goal of the paper to get good, like good timing, good latency, like less latency than you would get with encryption-based methods. And something that you can see here is that Shredder is actually doing better than cloud-only execution. Like if you would actually just send the data straight to the cloud, you're doing better, although you're doing some computation on the edge device, which is weaker, but you're doing better. And the main reason is that the overhead is not the computation, it's the communication. And once you send the entire query, because the raw data is huge, it's going to have a lot of communication costs. But once you send an intermediate representation, which is normally smaller, if you like choose it from the last convolution layers, it's a smaller, then the communication cost is smaller. So you can see that like the dark blue here, for Shredder, it's always it's normally smaller than the one for cloud only. So that's where we get a speed up over normal execution. So yeah, this was also like something nice to get. And then we also like tried different cutting points, and we see that, okay, if you cut deeper, you're going to get better privacy. And that makes sense because the neural network itself is distilling the information, and it's kind of getting rid of whatever it doesn't need. So it's better to cut less, like from the later layers, but also there's diminishing returns, right? So you can just cut wherever you're good with the latency, your edge device can take it. And yeah, you can just like cut at the diminishing returns point and you'll be fine. So this was just to see where it's better to cut the network. So what was good was that you got faster execution, you got enhanced privacy. But what is bad is that this is heuristic based. You're like saving orders, you're like creating so many noise samples, you're then trying to learn distributions, maybe it fits, maybe it doesn't. And it also doesn't really offer that much insight, right? You're like adding some noise, but what does it really tell you? Like, does it really tell you anything? So we tried to kind of extend this into this other thing that is like more interpretable. And here we want to like we want to like get more insight. So what you want to do here is that we're saying that, okay, let's assume that we're not going to cut the network anymore. And we just have this image and we have this query. And within each query, there are some pixels that are more important and there are some pixels that are less important. So again, to the smile detection example, if I want to do smile detection, if I can like find where the smile is, and if I only send that, then that's much better, right? Then I'm not sending the extra information, so I don't have to worry about what's going to happen to it. And I'm only sending the smile, right? I'm only sending the important part. So what is important? What is conducive? Conducive is whatever feature that the neural network needs for carrying out its execution. So if I can kind of interpret what the neural network is doing, like which features it's using, and if I can only keep those, then I'm good, right? So I need to figure out what the neural network is thinking and what it's doing and act on that. So here, our intuition is that if we have this trainable noise mask, but here the noise mask is not like a static noise that I'm learning, it's the actual parameters of noise. So if you have like Gaussian distributions, this is the standard deviation. So if I can somehow train this noise parameter, the standard deviation directly, so that wherever it's like less important, the standard deviation is higher, and whatever is more important, the standard deviation is lower, then I can have a good estimation of what features are conducive and what features are not, right? Does that make sense? Does anyone have any questions? Okay. Okay, yeah. So here our goal is to kind of move with more insight, to like find what features the neural network is actually using and like train this noise parameters directly. And what we hope to get is that, and this is like actually what we got, is to see like for each task, what is the neural network looking at? So here, like for task of hair color detection, glasses detection, smile detection, you can see all the masks that the model we extracted from the neural network. And this is kind of, it shows what features the model uses. And these rows, each of them show how far we push the network. Like if we want the network to use the least possible amount of features, what are the features that it's going to use? But if we like allow it to use more features, then those are like the higher up rows. And you can see that this is kind of commensurate with what we think. Like we want to use hair color, we like look at the person's head. We want to see glasses, we like look at the eyes. We want to see smile, we look at the lips. So this kind of makes sense. Okay, so we want to get those. So what do we do? Here, as opposed to that one single noise tensor, we have two tensors. One of them is the standard deviation tensor, one of them is the mean tensor. And what we would do, like once we have them, so this is like right now abstract, we don't know how we're getting them, but if we assume we had them, then we take a sample from them, we get a noise tensor, we add this directly to the input, and we have this noisy representation that has suppressed like some of the unimportant, unrelated features. So how do we get them? Like how do we get them using backprop? So how can we like learn distribution parameters? That's not really intuitive. So to make this easier, what we did was we kind of did a small reparameterization trick. As opposed to sampling noise from the standard deviation and mean, we sample it from 0 and 1, but we multiply it by the standard deviation and we add the mean. So we kind of turn this into this like multiplication and addition that you can actually do backprop on, right? You can calculate the derivatives and train them. So this is how we make these two tensors trainable. But one problem here is that if we use SGD to train this, we might get negative standard deviations, right? The tensor B, it might become negative. So in order to kind of fix this and get this nice formation, get a well-formed standard deviation, what we do is first, we want to make sure that whatever we have is in a certain range. It's above 0. But we also don't want the standard deviations to go up to infinity, because what the network will learn, like this we came up with actually through experimentation, is that if you incentivize it to increase the standard deviations, what it's going to do is going to find one useless pixel and just keep increasing the standard deviation for that. And we don't want that. We want all useless pixels to have high standard deviation. So we want to cap it so that one of them doesn't really grow more than the others. So we put this tanh here so that we can say that, okay, the minimum has to be 0, the maximum has to be some number that we find through hyperparameter tuning, and that's it. You can't really go above this or below this. So this is why we did this kind of reparameterization trick. And what we do here, it's very similar to Shredder. We want to increase the noise. So we have this first term, first we want to keep the accuracy. So we have the cross entropy, but here we have to make sure that like at each training pass, we are sampling from the noise distribution. So each batch, like each sample in the batch is getting its own noise that is sampled from this distribution and added. So we have the cross entropy loss, and then we also want to protect privacy by adding more noise. So here, like we're directly saying, okay, I have the standard deviation, just like increase that. And like the log and like this weird looking, like why it looks so weird and why there is the log here is because like we also have this, like we show that information, like information theoretically, we are decreasing the amount of information. So that's why we need the log to just make the maths work better. But in practice, you can just put the like the sigma of the standard deviations without the log and it still works. And then we also have this lambda knob that again does the similar thing. So similar to Shredder, what we do first, we train the noise, but here we're training the actual sigmas and the means. So we sample, we train, we backprop, what we would normally do. But here we have an extra step too. So assume that we found our noise mask. We now know that like, okay, for this task, this like features are important, and I want to suppress the rest of the features. So how do I do that? One way is to just add a lot of noise, but adding a lot of noise, or we can do this, we can add a lot of noise, or we can just black out the features. We can set a threshold and say that, okay, if a standard deviation for a pixel is higher than like 5, just put black dots there. So both of these things, what they do is that it's kind of random. I mean, it's black or it's random, but still it doesn't care about what the network thinks, right? Like maybe if I put black, maybe that's not what the network is used to, right? Then I'm going to lose a lot of accuracy. So maybe all the images that it was trained on, they all had like, they were all outdoors. So if I put black, then it's like really not going to work anymore. So what we need to do is to somehow find representations that the network is used to. So we do a second kind of training to train the suppression values. Like what am I going to suppress with? We find these static values. So let me just show the example again. So like here for this like lady, you can see that for different tasks, we have these like, oh, the hair and the smile are in reverse, but like the lower and the leftmost, you can see that you can see her smile, but the rest of it is just, it's like some static suppression values. So this is what the network thinks an image should look like. And this is a static, right? So if it was anyone else's picture, this part of non-conducive features, it would be the same. We learn it and then we use it to suppress everyone's image. This way we're sure that we're not leaking any information, right? Because it's not changing based on the person. And we only send the lip, which is like needed for the model to get good accuracy. So we also have this second phase that we try to figure out what the model is thinking, and yeah, we train. So you can see all the results in the paper, but just to summarize, because so here we also compare to Shredder, and this is a bit better. And also it's really important that this one is applying the noise right to the input, whereas Shredder was like adding the noise to some intermediate layers. So that one was also getting some help from the neural network itself, because the neural network was decreasing some information. So here, although we are adding the noise directly to the inputs, we are getting somehow like there's little improvement. So, and it's also more understandable for us, right? We can just see the map, see what is being taken out, and just apply that. So I will not really discuss the results here. This is like we assume that there's an adversary who's like trying to guess the private features, and then we show that they can't. So so one fun result that I wanted to share with you, and it's not yet in the paper, it's that we applied this to the task of pancreas segmentation and pancreas detection. So far, the noise was a static, right? How we were learning it, like it would only learn that all smile detection images, like the smile is here. So if the image was maybe tilted, or if it was kind of out of distribution, then the noise mask would not match it. It's not dynamic. So here what we did was that we added this kind of interpretability model, is what we called it. It's like a small single layer model that you feed the input to it, and this one generates the tensor B, the standard deviations. So based on the inputs, you're getting this sense of dynamic noise. It's not, the noise is no longer just static. It's now dynamic, so the standard deviations can change based on the image, and it can find the pancreas and like put noise everywhere that there's no pancreas. So like you can see that like as we increase our threshold, like only the pancreas remains. All the other organs are, you know, being suppressed. So this was kind of fun.
So we have a couple of questions. I think
yeah, sorry.
Yeah.
Do go
Fennel,
on.
do you want to go first?
Yeah. So, how would the correlation between pixels factor in? Like, if say for smile, like a nose would be an important factor, but then like if the network blacks out the pixels of the nose, then the accuracy of the network would decrease, right? But like,
yeah, so this really depends on how much suppression you want to have, right? So if like let me go back to this So here, like the topmost, you can see that the nose is still in there. So on the left, you can see the suppression ratio and the accuracy loss. So here we are losing 0 to only 0.5% accuracy if we keep the noise, the nose, and we also are suppressing 70 to 75% of the image. But if you're like, okay, this is not enough, I want to suppress more. So the last line, you can see that the suppression ratio is 93% to 96%. We're only keeping the smile. Then here you're losing 5 to 10% accuracy. So this is like a trade-off, right? If you really want to like have the accuracy and keep the nose, then you're leaking nose information, but you're getting better, like 5 to 10% better accuracy. So this is kind of up to the policymakers to like make the decision what they want to value more. But you're offering the trade-offs here. Does that answer your question?
Yeah.
Okay, great.
Thank you.
Okay. Yeah, we had a couple more. Do you want to take them now, or should we take them?
Yeah, let's take them now because yeah.
Okay. Devdar?
Yeah, hi. So I might have missed this, but in the second method where you are actually adding noise to the image, do you train the network parameters after you train the noise parameters, or you do not?
So both of the methods, the network parameters are always frozen.
Okay.
And yeah, and something nice about the second one is that we also showing the paper that you can do it to black box access as well. So if you like, this is like in the case that the user wants to have all the control. So even if the model deployer is not helping you at all, they're not sharing their weights, they're not sharing anything, you can actually like apply this yourself and you don't need any collaboration from them. So everything is frozen. Yeah.
Right. So in a way, you are exploring the boundaries of your decision of the network.
Yeah, exactly.
So have you tried tried to link it to maybe generalization of a network or something like that?
No, not yet. Like, yeah, there are a lot of things that I think like you can use this for robustness to adversarial examples as well.
Yeah.
But yeah, we haven't tried those things. No. Yeah.
Okay. We had one more question. Prasanna?
Hey, like as I look at this work, intuitively it feels to me that you're doing image segmentation in some way. And I was interested in seeing if you've evaluated your model at image segmentation tasks. Like if there is a certain task for which you know, like for example, smile is always important. And if you have images where smile is labeled in image segmentation datasets, like it would be a good evaluation metric to see how you
Yeah,
do
no, we haven't tried it. So this pancreas one is actually pancreas segmentation. So the red one is actually the actual boundary provided by the model. And we saw that like, okay, what we're getting is really similar, but we didn't really like evaluate it with like, you know, quantitatively. So that's a really good idea. Yeah, we should try it. Thanks. Yeah.
And also like image segmentation seems to be like a tough task for which like large models have been built. I was interested in like, have you guys tried integrating those large models to generate your masks somehow?
So actually this interpretability model that you see here, like the blue one, this was like a unit that is used for, like initially it was a unit, right? And its units are used for segmentation, if I'm not mistaken. And yeah, so we started with that, but then we actually made it smaller. So right now it's like a single or like 2-layer simple autoencoder, linear autoencoder. So yeah, we could actually squeeze it to that small model. And yeah, you're right. I think that's probably a good idea. Yeah, we should explore it. Yeah.
I'd be very interested in seeing the results. Thank you.
Yeah, thanks. Thank you for the suggestion.
Yeah, I think we can move on.
Okay,
I don't
great.
see any other questions. Yeah.
So, so one other thing that I'll just, because we're out of time, I'll explain it quickly, is that because we're like removing some of the features, we thought that, okay, maybe we're also removing some features that were biasing the network before. So we looked at some fairness notions like demographic parity and equal opportunity, which basically they try to see how fair the model is with respect to like the subgroups, like gender. We were using gender here. And we see that like once we're using our method, the fairness metric values, so it's better that they're closer to 0. So they are getting close to 0. So it's kind of the model is becoming more fair. It's like we call it post-hoc fairness because the model is frozen, right? It's like after the model is trained, so it's post-hoc. And we can see that like without changing the model, you can actually get better, like more fair results. So that's also interesting that like removing some of the features, it shows that those features are probably biased and those are what was biasing the model. So if you remove them and just replace them with some static values, you're getting a more fair of a model, which is kind of interesting. So talking about fairness, we also, we've done this, like it's this very small workshop paper that it builds on a previous paper by Eugene Bagdasarian. And what they did was this was kind of it is kind of a famous paper in the field of differential privacy for deep learning, is that they show that differential privacy is disparate. And what does that mean? Is that if you look at picture A here, so a non-DP model, there is a gap between like darker skinned people and lighter skinned people, the accuracy that you would get at test time. Now, if you apply differential privacy, this gap only increases. And the people who are getting worse were the people who were actually worse to begin with. So the poor get poorer. And this is because they are less represented, right? So if you have a data set that has small subgroups that have populations of like below 5%, then those people are really going to get stomped on when you're using differential privacy. And their accuracy is going to get it's going to get ruined more. So we show that like when you're using privacy, you're bound to lose some accuracy. But they show that when you're using differential privacy, this actually is worse for underrepresented groups that have less samples. So this is what they show, and they show that this is happening because of both applying noise and clipping. So they show that, okay, if you're not using noise nor you're clipping, you can see the accuracy in the top row here. The difference between the two subgroups are like very small. If you're using noise, the difference is a lot, but then it can converge. The same happens for clipping. But when you use them both together, then the model can't really recover from that. And that's because once you're only clipping, the underrepresented group that has to have higher gradients, and you can see the gradients below, it can only apply small ones, right? We're clipping to 1. So after iterations, it ends up applying it, and overall it does get the update that it needs, so you still get a good result. Same goes for the noise. The noise is not that much, so the model can converge. But once you have them together, you're clipping to 1, your noise, the standard deviation is 0.8. So whatever update you're giving, like that noise is gonna override it. So for people who have like less representation, less samples, they can never recover from this. So this is why you see this huge gap. So this is what they showed, and what we showed. So they only did this for like, they tried it for like class imbalances of 5% and below, and they only tried epsilons of, I think, 1 to 10. So it's kind of like good privacy and like a very small like actually a very large imbalance, like a high, like the minority was like really small. It was like 5 to 1%. So what we wanted to try was to try like a wider imbalance rate, like 30% to 0.1%. So because that's more realistic, right? Even in smaller tasks, it happens like we have a 30 to 70 imbalance. So we wanted to try that. And we also wanted to try epsilons higher, like 16, because in real life, like when you're applying differential privacy, it's really hard to get good guarantees. So maybe you're getting some actually like meaningless guarantee, like epsilon of 16 or like high epsilon. So we show that, okay, if you do it like you have a high epsilon and you're not that imbalanced, you're neither fair nor are you private. So you'll end up losing fairness. I mean, you end up getting disparate results between the subgroups, and you also don't really have the privacy. Like your epsilon is 16. So if you're not careful when you're applying these methods like differential privacy, what you're doing can have huge implications. And especially if you're like dealing with census data or like some sensitive type of data. So we should really be careful. And this like fairness issue is like huger than what we would think. It doesn't happen only when you're applying rigorous privacy or like once you have very small subgroups. It can happen in any type of data, and yeah, we should be more cautious of this. And yeah, with this, I'm gonna kind of conclude the talk here, that we saw some interplays of utility and privacy and also fairness. And some of the things that I'm exploring right now are privacy preserving methods for different NLP tasks, and also how can we like try to mitigate this fairness issue that happens with like privacy, and specifically with differential privacy. If there are any more questions, I'd love to answer them.
Thank you. Awesome. Let's start by thanking the speaker. Let's all unmute ourselves and yeah, and just thank the speaker first.
Yeah, it's kind of the inverse.
Oops.
Um,
I think I muted you too by mistake. Okay, so yeah, now that we are back. So yeah, anyone who has a question, feel free to raise your hand or put it in the chat. Okay, Akanksha?
Great talk. Thank you so much. One question I had, and this is more open-ended. I imagine a lot of these noise addition methods could be used in different domains. And specifically the second work, which looks at basically, only adding noise to the, parts of the input that is being used by the neural network. How would something like that play out for non-vision based models? I feel like understanding when what kind of features are being used in the neural network is easier for vision. Not easier, it's just a lot of people have worked on it. But other domains that are maybe NLP, I'm not sure, but other domains like mobility and system domains, what are your thoughts on that?
That's actually like a really good point that you raised. Yeah, I agree that there is more work in vision, and I have felt that. And also it's easier because you're dealing with something that like each pixel is continuous, right? So it's really easier to deal with it. But once you get to NLP, you have a discrete domain, right? You have words, like what does it mean? And the words can like move places. So I agree that it's like way more difficult. And so I have just like, I've been working for like on NLP and privacy for like 3-4 months, and the closest thing that I can think of to what you said, like finding which, like how the noise can be added or which features are important, I can't think of anything that really like focuses on figuring out like, so we have attention mechanisms, right? That you can like say, okay, right now the attention, there are some papers, they argue that the attention that is used in NLP tasks, the attention mechanism in recurrent neural networks, that is actually a way to interpret the model, right? You can use this to see which features are important for like at which time step, and then use that as like kind of a thing to say that, okay, right now this one is more important. But there's also this more recent paper that shows that you can train the model in such a way that the attention mechanism actually points to something that is not related and still get good utility. So this is one thing that I can think of. But about the noise, there are some recent papers from Amazon, and what they do is they want to apply differential privacy to NLP tasks and basically to embeddings, to word embeddings. And what they do is that, so normally like how do you add noise to a word, and like what does it mean? So what they do is they take the embeddings, which is like a vector that represents that word, and these embeddings are usually in a way that similar meaning words that they are near each other. So increasing them is going to throw you off to like a nearby word. So they add noise, but they condition this noise. They kind of multiply it by the distance. So they try to minimize the noise and like add noise that only throws you to similar meaning words and doesn't like, if you say, I don't know, if you say pizza, it doesn't turn pizza into ocean. It turns pizza into pasta, you know? But yeah, these are like the only things that I can think of. But I haven't really seen much work in this area. It's way more underexplored compared to vision and like normal private statistics. So it's really interesting to study.
Right. Awesome. Thank you.
Thank you.
Yeah. Does anyone else have a question? Yeah. Feel free to raise your hand, or you can just unmute yourself too.
Hi, I do have one question.
Okay.
So how does all this work out when we have data sets with very low resources? Specifically where already you're trying to clip gradients and reduce the impact of each training example, correct? But now when we take data sets where each of our samples is really important, and then we end up clipping these gradients during training, what exactly happens? Don't we lose out on a lot of important information?
So so differential privacy and differentially private deep learning, it really doesn't work well when you have little samples. You have to have a large number of samples. Otherwise, you're going to lose a lot of utility. You're not going to get anything out of it. But so there is like also like the triangle that I showed you. There is another famous triangle. It's like privacy, utility, and sample size. So the higher like number of samples you have, you can get better privacy with less loss to utility. So it's really good to have more samples. And if you have less, then you're bound to lose more accuracy.
Okay. Thank you.
There is this paper called No Free Lunch in Privacy. I think that paper discusses this as well. So if you want to...
Can you just repeat that again? I didn't get it. What was the name of it?
I'm going to write it down actually here in chat. It's called No Free Lunch in Data Privacy. I think it's this, but if you Google it, it's going to show up.
Okay, all right. Thank you.
Sure.
Okay, do we have any other questions? So I had one question about the, I think it's more high level, but I was wondering why like distorting the input, like doing an irreversible change to the input is like it's going to be better than a reversible change. So like you could do reversible change, like there's this new work in NLP called neuro-linguistic steganography. And what they do there is they sort of use a pre-trained model, and they use that pre-trained model to convert a piece of text into another piece of text. And this process is fully recoverable. Like if you have the weights of the model, you can like fully recover the original piece of text. So I was just wondering, like why is distorting the input the way to go here? Like where is the bottleneck with these reversible methods? Like where is the efficiency bottleneck with these reversible methods?
By efficiency, you mean like how do we know that it's not reversible? I didn't.
Oh, so my main question was so you mentioned that adding noise is going to be like faster than like cryptographic methods, which I guess are reversible. So I was just trying to understand like what is the main bottleneck in cryptographic methods, because in those cases I think the you can recover the input exactly again, like
okay, let me try to like break your question. So one difference, this is not in terms of efficiency, but one difference between like crypto method and information theoretic method, it's the difference between security and privacy. Okay. So there you have security, and once you have security, it's good, you're getting your privacy. But the problem is that if you train a model using like crypto, so you're like training a model encrypted, the data itself, if it's getting memorized before, it's still getting memorized now. So it doesn't help the inference, like not that inference, like the information you can infer, it doesn't help the information that leaks. It's hiding it from you, but the information is still leaking. So that is the problem, like with the whole philosophy of the thing. So if you like train a model using encryption, you don't have guarantees for people's privacy, because my credit card number can still be memorized in there. I don't see it, you know, like it's protected, but it can still be in there. So if someone queries it, because once you query them, then finally at some point it gets decoded, right? Then that person still gets to see my credit card number. So that is the difference with like the privacy and security part of it. But about the inefficiency, I don't really know that much crypto myself, but what I've seen is that the problem is mainly with, so if you have like, if you're inputting a vector of a size 100, they apparently have to append some stuff to it. So they make it like, so like 1 bit becomes 64 bits. And then all the multiplications and everything is done for all the 64 as opposed to 1. So they make it bigger, and therefore they have to do more computations. So this is one problem. And another problem is that like most of them only work for linear computations. So when you get to ReLUs and stuff, they have to approximate them using polynomials, and a lot of problems happen there. So this is the only thing I know. I just know that it's much slower because of this, but I'm not sure why.
Okay, yeah, thanks. That makes sense. So I'll just ask around for anyone has any other questions, and if not, we can stop the recording. Okay, cool. So let's thank the speaker once again by unmuting ourselves, and I'll stop the recording.
Great job.
Thank you.
Thank you. Yeah. So I'll just stop the